Hi, this is the last lecture for the process basics topic. Previously, we introduced to you the concept of a process, and then we talk about fork, wait, and exact BP. So in this last part, we talk about shared memory. In all previous example, those concurrently running processes run independently. Once a child process is created, there's no way to communicate with it. In other words, as defined by the fork system call, the parent and the child processes are running independent and separate address space. They do not share anything. But we create multiple processes to work on the same task. Hopefully, they run concurrently to solve a problem for us. As a result, frequently, these processes must share something. For example, process A creates process B for B to compute something as a result. Then how could A get this information back from B? You might want to say, let me write the results to a file. That is fine. But we hope to have more efficient sharing. And this is the concept of shared memory. Shared memory or shared memory segment is a piece of memory that can be allocated and attached to an address space of a process. Only those processes that have this memory segment attached can have access to it. A process that does not have this shared memory attached won't be able to use it. But because we have something sharing, remember, we repeat so many examples for the concept of concurrent sharing. That is, multiple processes try to access a shared item in an interleaved or concurrent way, something bad could happen. We have explained this several times. For example, at the very beginning, we explained that a process does input output, then its execution has to be terminated, suspended. And then when we start two processes from a single terminal window, they share STT out. As a result, if you do not take care of this sharing, both processes could print the results to the same STT out. That is, you have mixed output line, something from a process, something from the other. So this is a precursor for you to understand race conditions. This race conditions are really, really a big headache to concurrent computing. So let's make our question and the solution short. How do we get a shared memory? There is a standardized sequence. First of all, we find a key. This key is used for identifying shared memory segments. Actually, in Unix, there are many stuffs are identified by keys. So first of all, we find a key. And then with that key, we use the system call share memory, share memory get to allocate a shared memory. Once the shared memory is allocated, always remember this shared memory is allocated outside of your address space. Then we use share memory attach to attach the shared memory to an address space. Then after that, you can use it. So the combination of share memory get and share memory attach is very similar to the malloc function and clf function you are used to in C. So after that, you could use the shared memory, putting something into shared memory and retrieve something out of shared memory and so on. After using the shared memory, use share memory detach, shmdt, to cut the shared memory segment off your address space. After that, you cannot use the shared memory again. If you wish to use it again, attach it into your address space. So the one who created or allocated shared memory by the use of shared memory get must deallocate it with the shared memory control system calls. So what you need are 5 steps. Find a key, allocate the shared memory by calling shared memory get. Attaching a shared memory to your address space by calling shared memory attach. After using it, call shared memory detach to cut it off from your address space. Finally, if you are the one who allocated that shared memory, you have to use shared memory control to remove it from the system. So we will talk about each of these 5 steps. Then we look at several examples. Just like when we want to use fork system call, we must include the system types. The second header file, ipc.h, must be included. IPC in Unix means inter-process communication. This IPC stuff contains many defined constants and so on. Then, if you wish to use shared memory, also include share memory.h, shm.h. So always include these 3 header files at the beginning of your program. So what is a key? A key is a value of type key underbar t, which is usually a large integer. Although occasionally, if you are a system administrator, when you allocate shared memory, get a key, well, that value may be a small one, but usually it's a rather large integer. You have 3 ways to get a key. The first one is do it yourself. The second one is by calling a function f2k, file to key. This function will return you a key. And finally, you can ask the system to provide you with a private key. Why do we use it? Well, it's very simple. As long as other people who know the key value, they will be able to use your shared memory. So sometimes to keep your shared memory in private, you could ask the system to provide you with a private key. We will talk about it later. Now, let's take a look at the first one. Do it yourself. Just declare a variable, some key of type key underbar t, and put an integer into it. So you have a key. of type key underbar t. But this is usually risky. What kind of a number you want to put into it? Your social security number, your birthday, or whatever. So it's not so secure. Most people would take the second approach by calling the F2K function file to key. So the file to key or F2K function requires two arguments. The first argument is a path, a string. The second one is usually a small integer. So if you insert a path here, a small integer here, F2K will return a key. So here, usually the path is simply the current directory dot slash. Why? It's because we have our program in the current directory, and we run our program from there. So that current directory belongs to me. As long as all of my program to be run concurrently are from there, nobody would have access to that current directory. So dot slash is a safe way to specify this path. The ID is a small integer. Usually we just use a character there. So here is an example. I use the current directory and the small integer F2K will return a key stored in here, some key. Now, always remember this is so important. Keys are global entities. Here, global does not mean global to your program. It means it is a system-wide entity. If other processes know your key, they can access your shared memory. So global here means global to everyone in the system. So as I mentioned earlier, you could ask the system to provide a private key with this keyword IPC underbar private. We'll see an example using it. So a quick summary, the recommended way to generate the key is by calling the F2K function. The first one is a string leading to your current directory dot slash, followed by a small integer. F2K returns a key of type key underbar t. Then let's move on to the next step. Share memory get. That is, allocate a shared memory. So always remember to include these three lines. So share memory get allows you to make a request to allocate a shared memory. It takes three arguments. The first argument is the key you produced from calling F2K or whatever way. So the first argument is a key. The second argument is the size of the shared memory you wish to allocate. The third argument is a flag. This flag indicates two things: whether you are going to create the shared memory or you are just want to use the shared memory. Now, once you have a shared memory, you can also specify permission, how that piece of shared memory will be used and by whom. Now, I am sure everyone knows in Unix, a file will have some file permission: read, write, and execute, R, W, and X. So if you don't remember this, we will talk about it later, a few slides later. So this flag, if you are going to create the shared memory, use IPC underbar CREAT, no E. This is a bitwise OR followed by 0666 for creation. Of course, you could change this permission 0666 to something else. So let's just say 0xxx, where is x is an octal number from 0 to 7. We will talk about it later in case you forgot what the Unix permission is. So if you wish to create a shared memory, use this part. Or if you want to get the shared memory just for use it, that means the shared memory have already been created by someone else who used this as the third argument. And for you, a process that just want to use it, then remove this part. That is, remove IPC, create in vertical bar, and just use 0666. So when you call share memory get, you provide the key and specify the size. Again, always remember, use size of function rather than a number there. Finally, we have a flag. This flag is either creation or use. For creation, use this, and for use this. And you may change the permission here. So after specifying the three arguments in the call to share memory get, share memory get will return you a share memory ID. This is just like when you create a process, the system assigns that process a process ID. So the idea is exactly the same. Of course, share memory get could fail. In that case, you will get a negative value. It's just a Unix convention. So let's say we have a data structure, data, in which we have an integer, a double, and a character. And a process wish to create a shared memory that is large enough to hold this data structure. And then shared memory get would return an integer, which is the shared memory ID of that piece of shared memory. So in this call, the first argument is private key. IPC underbar private means asking the system to provide you with a private key so that no one would have a key that is identical to this private one. And then size of this data structure. And the third argument means I am going to create or allocate this shared memory. If the call to share memory get is successful, share memory get returns the shared memory ID stored here. So this is the use of private key. Now, what if you wish to generate a key for your shell? Let's use the same thing. Now, if you wish to generate key, then you have to declare a variable of type key underbar t to hold that key. Then we call f2k by using the current directory and a small integer as two arguments to f2k. And f2k would create a key value stored in the variable key. And then you insert the key variable here and the size and creation and so on. Then share memory get would return the share memory ID to you. So this is that easy. Now, let's refresh your memory regarding Unix permission. So 0666 is an octal number. An octal number requires 3 bits. It goes from 0, 0, 0 to 1, 1, 1. So 0 to 7 in decimal. So what does that mean by this? So each of these 666 is an octal number. When you specify an octal number, you have to add a prefix 0 there. If you don't add 0 there, it makes 666, which is wrong. Now, as I mentioned, 066 is an octal number. Each of this, excluding this 0, each of this value is an octal number represented by 3 bits. So 066 representing in binary would be this. 0 is an indication that this is an octal number. So the first 6 is 110, the second 6 is 110, the third 6 is also 110. So these 3 group indicates the permission for you, the permission for the group you are in, the permission for everyone in the world as long as they are able to access the computer you are using. So repeat, 666 represents 3 groups of permissions. The first, the leftmost one is you. The second one is the group you are in. For example, suppose you wish to develop a software project in a group, and the group member would have, say, 5. So you could ask the system administrator to add all 5 of you into a group. Then this is the permission for your group to use. And this is everyone in the world as long as they have the chance to access your computer. So because each octal number has 3 bits, the meaning of 3 bits is the first one is readable, the second one is writable, the third one is searchable or executable. So you probably are used to R, W, and the X, right? When you use the command change mode, CHMOD. So let's interpret this one. It means you, the programmer who calls this shared memory get with 0666 here. It means you can write, you can read, you can write, but you cannot execute the things in that shared memory. And your group can do the same, and everyone in the world would be able to do the same. Now, what if you want to say, hey, if you allow everyone to have access to your shared memory, that could be risky because hackers could put something bad into the shared memory. So what if you wish to disable this feature so that no one in the world is able to access this shared memory? You just replace to 0, 0, 0. So the permission here would become 0660. Now, what if you think this shared memory belongs to you and all processes created by you, and it's none of the business of your group? So you could disable in this way 6 still you, and 0, 0, 0, 0, 0, 0. So the permission here will be 0600. Now, let's do one more thing. What if you wish the following? You allow the members in your group to read, but they are not allowed to write. So your group permission should be 1, 0, 0, right? 1, 0, 0. What is the number corresponding to this 1, 0, 0. In decimal, that's 4. So if you would also allow everyone in the world could read but have no right to write, so it's going to be 6, 4, 4. This is usually how you set up a folder so that people can read but cannot write and cannot search. So this is a thing you have to remember. Of course, when you create shared memory, you don't want everybody to read and write. You probably only wish to have you yourself to read and write. So that's going to be 0, 6, 0, 0. And if you wish to allow your group to read but no write, that is 0, 6, 4, 0. Now, what if you would allow your group to write, but no way to read? That's kind of interesting. So that is in your group, no way to read. It's going to be 0, 0, 1, 0. What is it? Isn't it 2? So the setting will be 0, 6, 2, 0. So please make sure you understand this. So that's the meaning of this permission. Then if the return value of shared memory get is less than 0, which is a Unix convention, the request was unsuccessful and no shared memory is allocated. Why? Shared memory get would return negative value. It's because Unix could not find any available memory for you. It could be due to you specified a incorrect argument. For example, the size of is too large. The system does not have that much memory for you to use. Or when you want to create a shared memory, you only use 0666 and forget to put this part there. Or when you want to use the shared memory with 0666, but the shared memory has not been created, and so on and so forth. Therefore, if shared memory get returns 0, it means something wrong. Major reasons are mentioned earlier. So remember this. Create the shared memory before its use. Now here's an example. Suppose I have 2 processes. Process 1 tries to create a shared memory for process 2 to use, and this shared memory will be shared between process 1 and the process 2. Therefore, process 1 generates a key and specifies the size. Because this is a creation, it uses IPC create followed by 0666 or whatever permission you want to put there. If this shared memory get was successful, a shared memory will be allocated outside of your address space. Remember this, shared memory created is not in your address space. Instead, it is outside of your address space. So now you have learned how to create a shared memory. Then, how can we pull an allocated shared memory into your address space? This is the call shared memory attached. Now, because the shared memory created is not in your address space, you have to port it into your address space so that you could have access to it. So the call to shared memory attach also requires 3 arguments. The first argument is the shared memory ID returned from shared memory get. Because this is an introductory course, the second pointer is, the second argument is a pointer. Here, we just use null to save your time. And the flag here means several switches when you want to attach a shared memory. So please just use 0 there. So basically, in this course, and in particular for your programming assignment 2, you just put the shared memory ID here, followed by null, followed by 0. That is easy. So if your shared memory attach is successful, shared memory attach returns a void pointer to the shared memory segment. If unsuccessful, shared memory attach returns a negative integer, and that is Unix convention. So let me quickly go through it. After you allocate a shared memory get returns you a shared memory ID. Then you have to pull the shared memory into your address space. To do so, you call shared memory attach with the shared memory ID returned from shared memory get and a null and a 0 here. If it's successful, shared memory attach returns you a void pointer to the shared memory get. But why shared memory attach could fail? Well, one major issue is when you try to attach the shared memory, it's not there. Or due to whatever reason, the shared memory has been removed. Or your shared memory ID is an invalid one. These are major reasons I have found throughout the years in student programs. Here's an example. I still use this data structure and the shared memory ID key, then I need a pointer to the shared memory segment, which will be used to contain this data structure. So again, I use the current directory with a small integer. F2K returns a key value. Then I use this key, the size of this data structure, followed by creation. Now, if it is successful, then shared memory get returns a shared memory ID. Here, because of space limitation, occasionally I skipped error checking, but in your program, you have to do that. Otherwise, there could be some serious consequences, which will be mentioned to you at the end of this lecture. So after getting a shared memory ID, then we have to attach the shared memory into the address space. So we call shared memory attach. The first argument is shared memory ID followed by null followed by 0. Now, the returned pointer from shared memory attach is a void pointer. Void pointer is usually used as a like a placeholder or something. You have to cast type back to the correct type because this shared memory is created for this data structure. Therefore, I have to cast the returned void pointer to a pointer to this data structure and saved the casted pointer to P. But again, we have to watch for whether shared memory attach was successful or not. Now, if shared memory attach was failed, then it returns a negative value. So here we have already cast the address to a pointer to that data structure to test to see whether the return value of the shared memory attach is negative. So we have cast back to integer and do a test. Now, if the return value is not negative, then we know we have obtained a valid shared memory, which is also attached to my address space. Then I could put information into it. So I save 1 to variable A, save 5.0 to variable the double B, and put a character dot to the character X. So right after you get the pointer from shared memory attached, all subsequent use of this pointer is just like what you have learned in C for malloc and cmalloc. So remind you, you have to cast the pointer back to the correct type. And you have to test to see whether the return value is less than 0. Of course, you can always save it. You can always save to a pointer or save to the cast to integer, test it, and if there's a valid one, cast to the right pointer. That is your choice. Now, here's an example. We have mentioned that process 1 obtain the shared memory segment here. Then process 1 calls a shared memory attach. And assuming that the shared memory attach was successful, a pointer to the shared memory will be saved to the variable PTR. So PTR would have a pointer to the shared memory. After the creation of the shared memory, process 2 could also do the same. Process 2 does not want to create it. Instead, process 2 only wants to use it. So process 2 will specify essentially the same key, and then we use 0666 here. Now, you see why the use of current directory becomes so crucial. Assuming that the binary process 1, process 2 are run from the same current directory. So that // would be the same. And then if process 1 and process 2 use the same small integer, say process 1 uses the character X, process 2 uses the same character X, then it is guaranteed that when F2K receives 2 identical arguments, the returned key would always be the same. And as long as there is one argument that's different, then F2K will produce different keys. So here, process 1, process 2 must go through the same process to generate key and use the same size. But for the creation, we add IPC create. For the use, we use 0666. Now, after successfully get the permission to use the shared memory, then process 2 receives shared memory ID. Then process 2 uses the shared memory ID followed by null and 0. Now, if this shared memory has been created, shared memory attached from process 2 would return a pointer to the shared memory. So the pointer variable PTR in process 2 would also receive a pointer to the shared memory. But I have an interesting question. My question is, now, after process 1 successfully attaches the allocated shared memory into its address space, process 1 receives a pointer. And process 2, when it successfully attaches the shared memory into its address space, process 2 would also receive a pointer to the shared memory. So my question is here, are these pointers the same? In other words, PTR, pointer PTR in process 1 and PTR in process 2, do they have the same address? Please pause and give it some thought. When you get your answer, then please continue. Okay. If your answer is yes, in my experience, most students in this course will say yes, because the pointer points to the same location, the same address, the same shared memory. So it's supposed to have the same address. That is a logical thinking. But indeed, this is wrong, because process 1 has process 1's address space. Process 2 may have a totally different address space. Let's take a look at example. Suppose I have 3 processes running, and each process has this address space. You have the code section, data section, heap, and the stack. This process also has these 4 sections. Process 3 would have the same. So 0 is the first byte of this address space, and max is the last one. So we allocate a shared memory here. Remember, shared memory allocated just outside of your address space. So when this process pulls this address space into its address space, when this process pulls this shared memory segment into its address space, it will be here. It's not going to be pulled into your address space. It's going to be outside your address space. So the pointer received by this process is here. Now, this process is smaller. So when it pulls the shared memory into its address space, the pointer would points to here. Now, this is a much larger program. So the pointer returned from shared memory gets here. It points to here. So as you can see, these 3 pointers would point to different location. Okay? Although these 3 things are the same. Now you may want to ask me the question, how could this be done? I am sorry. I can't talk about too much here. You will learn it in an operating system class. For an example, let me spend a minute or so to talk about it. Most modern hardware would use the paging for memory management. So all a process address space will be divided into multiple pages. A page table of that number of pages will be allocated somewhere in the system. So your address will be translated using that page table to find the actual page that contains the information in your program. So a shared memory is also divided into pages. So those pages would simply be inserted to your page table. So each process would have their page table increased by a few entries. All of those page table entries points to here. So that means a larger process would have more entries in its page table. When you insert more page table entries pointing to shared memory, well, it's of course would be inserted to the end. The same reason indicates that if for a small process, it has a shorter page table, those page table entries pointing to the shared memory would be added to the end of that shorter page table. That is to mean that these 3 pointer even though they allow you to access the same shared memory in each program, the pointer in with respect to this address space and this space and this space are different. So now, after share memory get and share memory attach, right after you get a pointer from share memory attach, you can use that pointer as if you get it from malloc. Now, after using it in C, you free it. But with shared memory, the way to free it is different. Only the one who allocate that shared memory with IPC create has the right to remove it. For other processes, after using it, you have to detach it. How to detach it? Simply call share memory detach with only one argument. That is the pointer returned by share memory attach. After the execution of share memory detach, that share memory segment is no more in your address space. You have no way to use it again. What if later in your program, you want to use that piece of shared memory? Simple, attach it again by calling share memory attach with the same share memory ID and not in 0. So the one who created the shared memory with IPC create must call share memory control to remove it. Here, you just put the share memory ID returned from share memory get, followed by IPC remove ID, followed by null. So in this case, after the execution of shared memory control, that shared memory segment will be deallocated from the system. It can no more be used. Now, let's take a look at a very simple example, but also requires you to think something. So here, I have a program. Argument, counter, argument, vector. So I have a pointer, share memory. I have a share memory ID variable, share memory pointer, and the status and the AP ID. So here I call share memory get to get 4 integers. What do I use this 4 integer for? I would use this 4 integer to save my PID and 3 arguments from ARGV. And then this is a creation, IPC create. Now, I want the system to provide me with a private key because I don't need it to know it. So this share memory get, please add error checking, returns a share memory ID to me. Save in share SHM ID. Then I could use share memory ID followed by null and the 0 here to attach this share memory ID of integers into my address space. Because this is an integer array, therefore I cast the void pointer to integer point and save to the shared memory pointer. Don't forget to do error checking. So now after this pointer is obtained, you can use as if it's a pointer from a malloc. So get my PID. Remember what this means? Get my PID and save to the 0th location. Convert the first argument, second argument, and third argument to an integer, and save in the first location, the second location, third location. So after that, all 4 integers in the shared memory segments are filled. Then I'm going to do something interesting. I call fork to create a child. So if after forking and the get PID, if the return PID is 0, then I call the function. This function is supposed to be executed by the child process. When this function returns, the child exit. Now, if the return value of fork is not 0, remember to check whether the return value is negative. So assume that the fork is successful, then PID would be the process ID of the created child process. Then this main program or the parent process waits for the completion of the child. When the child completes, the main program or this parent process detaches and remove it, and finally this program exits. So this is a portion of a program. Then let's take a look at the child function. The child has a single argument pointing to the shared memory. Then the child is so simple. The child function has a integer pointer to shared memory. It simply prints out the value of shared memory 0, shared memory 1, shared memory 2, shared memory 3, and then returns final exit. Now the question is, why are shared memory get and shared memory attach not needed in the child process? This function is run immediately by the child. But how come it did not call shared memory get and shared memory attach? Think about it. Please pause. When you get an answer, then resume. Okay. I hope everyone figures out the answer. The answer is so simple. Reload a single program. When this program forks, the parent and the child receive exactly the same contents, including the pointer to the shared memory, right? Therefore, the pointer to the shared memory has to be the same because it's copied from the parent. And also because the parent's address space and the child address space are exactly the same. Therefore, the shared memory pointer would be the same. However, remember this won't happen usually. It only happens to this very simple program. Now, let's take a look at a larger program. Let's define a few constants: not ready, filled, and taken. In other words, in this program, I am going to create a shared memory to hold 5 integers. The first integer is a status. The next 4 contains 4 integers, actually coming from the ARGV of the coding program. So not ready means the shared memory is not ready to be used. Filled means all of this information have been filled successfully. Taken means the data saved to these 4 locations have been successfully retrieved. So we are going to write 2 programs. The first program is, I call it server. It's not the client server computing. I simply use the word server because this program will save information into the shared memory for the other program, the client, to retrieve. So this is my main program. So we used F2K to generate a shared memory key. Remember, I used the current directory here and a small integer x. Then use this key and size of that structure followed by creation to call share memory get. It would return the share memory ID, which in turn is used in the call of share memory attach. Share memory attach returns a void pointer, which has to be casted to a pointer to the structure memory and saved to share memory pointer. So after this, we have successfully created a shared memory and received a pointer to it. So the next part is the core of this program. First of all, we set the status to not ready, indicating I just got shared memory, which has not been initialized. So the status currently is not ready. Then I get my PID and save to data 0 for the remaining 3 arguments, each of which is retrieved from the argument vector, converted to integer and saved to data position. So after this loop is done, the 4 entries in the array data are filled, and the status is changed to filled, indicating that, okay, I have everything filled. Then we proceed to this while loop. We check the variable status. As long as the variable status is not taken, this program will suspend its execution for 1 second. Remember the meaning of sleep? Sleep is a system call. When you call it, your program or your process will be suspended for at least 1 second. So after 1 second, this process goes back and checks to see whether the status is not taken. You may want to say, how come the status could be changed to taken from field when I'm running there? Well, the client will change it. So this is your first example to see some communication between 2 processes. So if we can break this while loop, it means the status is taken. Then I print out, look at here, you should not use printf. Check the previous slides for the reason. So this program, the server prints out my body is the first number, followed by data entry 0. That is, we print out data entry 0. What is it? The server will put its IP ID there. Then this program who create the shared memory detach it and remove it and final exit. So this program is very simple. It creates a shared memory, attach it to its address space, and then set the status to not ready. After that, the server program filled in the 4 data entries, with data 0 being the PID of the server. After filling all 4 entries, the status is changed to filled. For every second, the server program checked the status variable to see whether it's not taken. If it's not taken, sleep for 1 more second. continue this shifting until the status variable becomes taken, which means the client, the other program, has already moved all the information out of the shared memory. So the server program will print out my body is from data 0, which means the client would put its PID into data 0. Then this server detach the shared memory and finally remove it. So this is the server program. Now, let's see the client program. Now, look here. We assume that the server and the client run from the same current directory. So we use // and we use the same small integer because these two arguments in the client and in the server are the same. F2K always generates the same key. But when this client calls share memory get the same key, true, the same size, true, but it can only use 0666. It cannot use IPC create because if this client use IPC create, the system would return negative value because that shared memory with the same key has been already allocated. So this shared memory get returns the shared memory ID. And we use this shared memory ID to call shared memory attach. It would return the shared memory pointer, which has to be cast back to the correct type. Then, now, the client must wait until the status is filled. Now here we use busy waiting. This is so busy. This is not filled, then we go back, check to see, not filled, not filled, not filled. This is a not very good way to write program. In the server, we use sleep 1. But here, it's so busy. This loop is a CPU hog, right? If the server is very slow to set the status to filled, but because this program is so simple, after the server allocate a shared memory and put information into data 0, 1, 2, and 3, it takes very short time. So it takes very short time to break this while loop. So once we break this while loop, it means data 0, 1, 2, 3 have been filled with values. So this client process just print out this one, 0, 1, 2, and 3. Okay. After printing the values in 1, 2, and 3, notice here, this data 0 was filled by the server with the server's PID. And the data 1, 2, and 3 are from the server's command line arguments. So in return, this client gets its PID and save it back to data 0, and then set the status to taken. When the server detects that the status changed to taken, the server would print out this value. But of course, for the client, after this taken, the client does not need the shared memory at all. So it simply detaches and exit. So the client is very simple. The client also try to get the shared memory, but it gets the shared memory to use. Then the client waits for the status of that shared memory to become filled. Then print the information out, save the client's PID back to data 0. Finally, it changes the status to taken. After that, shared memory is detached, and the this client ends. So far, we have written two programs, one server, the other client. How do we run it? Warning, the server must run first to prepare a shared memory. If you run the client first, or if you run the client faster, when the client executes its shared memory gets with use 066 without IPC create, its shared memory get will fail because the shared memory has not been allocated. So the server has to run first in order to prepare a shared memory. So what you can do is you open the terminal window and run the server. And then open a second terminal window, change the directory to the same folder, then run the client. It a bit later. It does not have to be very long, say 1 second or 2 seconds will be good enough. Then you will see that the server prints out its value. After the client prints out its value, the server will print out the client's PID. Or you could do something with only one terminal window. You run the server in the background. So server 135 ampersand, return. Then you run the client 1 second or 2 seconds later. So the server runs in the background, creates a shared memory, puts its PID into data 0, 1, 3, 5 into data 1, data 2, and data 3. And waiting, and then waits for the client to retrieve this information. When client runs, the client simply get the value out and put its own PID in. So this is your first example showing to you that with shared memory, two processes could communicate with each other through the shared piece of memory. This version uses busy waiting. The meaning of busy waiting is we use a very tight while loop, continually checking some condition. If it's not there, loops back. If it's not there, loops back. So this is a very tight loop, checking for a condition. Until that condition is met, then we get out. So this is referred to busy waiting. Without additional system features, we probably have to use busy waiting. Now, what if you wish to remove this busy waiting? Under Unix, there are features like the semaphores and the message queues. But another issue is because so many processes shared the use of a shared memory segment in a concurrent way, race condition could happen because we have we have a concurrent sharing. The results may be non-deterministic. So this is why we're going to talk about synchronization to build mutual exclusion and something else. When we reach that component, you'll feel kind of difficult if you missed a whole lot of idea and concept in the previous lectures. So here I have a few important notes for you to understand and to remember, of course. First of all, because shared memory segments are global entity, they belong to the system and allocated outside of your address space. And if you do not remove your shared memory segment, It will be there forever until the system is shut down or someone to remove it for you. In other words, if your program crashes due to whatever reason, before it can reach the shared memory control call to remove shared memory, then the shared memory will be there. So if your program frequently crashes and left so many memory segments in the system performance could be degraded by this extra memory as shared memory, because the system would have fewer memory for its own use or for other processes to use. So we need to know, one, let me put it this way, write your program defensively. Check errors in every step so that every time, even though you may have an error, before your program ends, whether your program ends normally or abnormally, always execute shared memory control to remove it. Now, if you fail to remove your allocated shared memory and you run your program many times, you will have a whole lot of shared memory segment left in space. Then IT may contact me and you'll be in big trouble because you make the system performance degraded. So how will you be able to know you have shared memory left in the system? There is a command called IPCS. Use the command IPCS to check if you have shared memory segment left in the system. Now, if you have found you actually have some shared memory segment left in the system, then use IPC remove command to remove your shared memory segments. So remember to use IPCS and IPCRM. Our grader will use this command to check to see whether your program would have shared memory segment left. After finish running your program number 2, you will have deduction if you have one. So how do you check shared memory? Use IPCS -m. It will list all shared memory in the system. So here is a snapshot. When I log into server Whopper, I am not sure whether Whopper is still there because I try to access it, always get denied. So the output will be, the first column is the key of that shared memory. This is shared memory ID and the owner of the shared memory. And this is the permission. And this is number of bytes. And this is the NATTCH means how many process has that piece of shared memory attached. We will talk about status on the next slide. So let's take a look at, we have a shared memory with permission 0666 of 12 bytes. This shared memory is owned by the user MACHOUCH. It has the shared memory ID this and the key this. But look at this column. It shows that no processes has this piece of shared memory attached. That means all processes that uses this shared memory are all gone. It means this shared memory is a leftover. Nobody's using it. So this guy, in particular, when you see 666 and just a few number of bytes, it means this person could have been a student in my class. So this one has how many shared memory segment left? 1, 2, 3, 4, 5, 6. 6. And this one has 1, and this one has 1. So that means this student or this user failed to remove its shared memory segment when his processes ended. Whether it's normally or abnormally, this user failed to remove the shared memory. So when you see number attached, it means, well, no one is using it. So definitely that's a problem. Now, I tried it again and log into Colossus. I'm sure many of you would use Colossus. So this is the output. We have the same output, the key and the shared memory ID, the owner. These two users are probably system administrator. Permission 600 means what? Remember? This shared memory can only be read or written by this user. And the size of it is 576 bytes. And this user has 3 processes using this piece of shared memory. And this user has a larger shared memory. Probably this user created 2 shared memory and also 3 processes to use it. And this GDM user also has 2 pieces of shared memory segment. And he and his group and everyone in this world could rewrite and execute. But the status is shown in this way, DEST. It means these shared memory segments are marked to be destroyed. So it's okay. So you know, from different server, when you type IPCS-M, you have different results. Furthermore, running your local system, your Linux laptop or desktop or Macintosh, your laptop or desktop, when you type IPCS-M, you may, of course, you may yield different results. So now, what if you know you have left some shared memory segment in the system? You have to remove it. By the way, our grader will not remove it for you. Our grader will run your program and check to see whether you left a few shared segment in system. And then our grader will deduct points and finally remove it for you. Then how do you remove your shared memory? Use ipcrm command. If you follow by -N, you use the shared memory key here. If you use lowercase m, you use shared memory ID here. Remember, you can only remove the shared memory segment owned by you. You cannot remove other people's shared memory segment unless you are a super user. So if I were you, I would do program number 2 in this way. First, write your program in a defensive way. Check all possible errors and make sure all execution paths in your program will eventually lead to the shared memory control to remove all possible shared memory segments. And if your program can crash for some reason, of course, if your program crashes, it means your program must have some bugs. So after crashing your program, type IPCS-M to check whether you have shared memory segment there. Of course, if you wish to do that, it would be much better for you to use IPCS-M before running your program. Or if you like, you could create a two terminal window and change directory to the same directory. In one terminal window, you type IPCS-M to see what are the current shared memory segment owned by you in the system. Then you move to the second terminal to run your program number 2. Then, while your program number 2 is running, you could type IPCS-M in the first terminal. You'll see how many shared memory segments have been created. After the end of your program number 2, issue IPCS-M again and compare to see whether you have extra shared memory segments there. If you have extra shared memory segment there, it means your program failed to remove it, which is a bug in your program. So make sure program number 2 is still easy, but tweaking your program to use shared memory segment and making sure all shared memory segments will be removed completely. Sometimes, to many of you who wrote program carelessly, could be a big headache. This is something I can't help you. You have to learn it from making mistakes. And then this is the end of our process discussion. Our next lecture will be on threads. After thread, we will move into the most difficult part, or the first difficult part in this semester. So my recommendation is dig up your discrete math book, or whatever book, or even calculus book. Refresh your knowledge about proof by contradiction, because we're going to use it throughout the whole semester. I can only teach you very little about it. You have to build yourself up. I hope you are ready for this proof by contradiction thing. So let's see you in my next lecture, the third one. Let me stop here and goodbye. See you next time.